Hello, I'm Sebastian Fischmeister. I will talk today about the convergence of safety and security in the connected vehicle space, some of the specific challenges and also some of the lessons that we learned over the couple of years now that we have been doing research in this particular area. Before we dive into the details of automation and some of the challenges, it's important to know that dependability always included safety and security. So already since the early 90s, people have basically lectured and told everyone that you need to build a safe and secure system. It's only in the last couple of years now that we built connected vehicles that security has become all of a sudden the center of attention again. In the talk, I will show always a couple of observations and then basically provide examples for this particular observation. One of the observations is that automation in the automotive sector has already a long history. It started more than 100 years ago, where the electric starter was the first task of a driver that got automated. So the driver no longer had to crank the engine and risk breaking the wrist or breaking the thumb. Then a couple of years later, the automatic transmission came to the market, and it accelerated much faster from there on with more and more innovation in the area of automating driving tasks. Like, for example, 1958, we got the first version of a cruise control. And then in the 70s, we got the first version of an ABS system with the sure brake system. In 1991, so now 30 years ago, we got our first distance warning and lane departure warning system in a debonair vehicle. In just 4 years later, we got our first cruise control system. Now, in this case, we had a cruise control with throttle control, and that means the vehicle was able to decelerate. It was not able to accelerate again, so it could hold its speed and decelerate. The reason is that the safety case for deceleration or holding the speed was doable at that particular point in time. Acceleration came later on. And more specifically, it came in the year 2000 with the first adaptive cruise control in the Mercedes S-Class vehicles, where the vehicle could basically follow another vehicle at a given distance in now a commercial vehicle. From there on, with the increase of computing devices in systems in vehicles and the increase of software in these systems, more and more features and driver assistance systems and automation became accessible. Like, for example, in 2003, Prius introduced the parking assistance system. And then, of course, in 2015, Tesla introduced the autopilot. Now you have also features like, for example, in other vehicles like Super Cruise, which essentially is intelligent highway driving or smart highway driving, where the vehicle can follow a particular vehicle and drive on a particular route that can, in certain cases, also allow it to drive off a highway and continue on regular roads between cities or sometimes even inside a city. The part that is important to notice here is that we did not jump from fully manual driving to a fully autonomous vehicle. It is a journey that has been going on for over 100 years by now. And as you can see in this figure, it started with the electric starter. And then, of course, at the beginning, it took a little bit longer simply because ICs weren't available at this point in time at that particular quality and with that particular compute power in the way that they're available now. And in the last 20 years, more and more features got automated. And when you look at this, you can think about the future trend. Well, the trend will be that more and more driving tasks or tasks of the driver will continue to be automated. And hopefully at some point we will get to our autonomous vehicle that everybody is marketing. Now, why is this important for the discussion of safety versus security? If you look at a vehicle from 1912 that had an electric starter, or even like later vehicles, you didn't have a lot of functionality that the attacker was able to attack. That's one particular issue. You didn't, especially not a lot of software inside these vehicles. The second part is that these vehicles functioned autonomously from other infrastructure. That means they had no connectivity to, for example, the cloud or to other vehicles. And that also caused attacks not to be really scalable. And we will talk about this a little bit later. But now that we have all these vehicles connected, and now that we have all of this software and all of these computers inside these systems, they of course now are susceptible to attacks and also to scalable attacks. So then, what are some of the challenges for safety and security and some of the observations? Well, one of them is that modern automated systems, for example, vehicles, are beyond deep comprehension of human minds. What do I mean by this? If you look at modern vehicles, you can see that they are very complex systems. Basically, a lot of people say that they are computers on wheels driving us around. Now here on this figure, you can see the growth of software in the automotive space and also in, of course, in general, the safety critical systems space. And you can see that in the 60s, life was great. Not only because we were all younger and because the music was better, it's also because at that time, the software for the Mariner spacecraft did fit on a single page of paper. Wouldn't that be great? Just printing all your source code today on a single page of paper and being able to read it through and then confirming that it works. Well, unfortunately, in the 80s, GM introduced software in the engine and in the controllers, and that with about 50,000 lines of code, and from there on, it has increased drastically. Ford right now claims that the Ford F-150 has about 150 million lines of code, and depending on which sources you look at across 6 citable sources that we found, you can see that you have about 30 to 100 computers, ECUs, in a modern vehicle. Now, the challenge for safety and security is there that we cannot comprehend really these digital complex systems. And the complexity is really the challenge that suddenly provides attackers a surface that they can exploit in some way. And the fact that we cannot comprehend these systems is very simply illustrated in the following case. If I ask you to build a bridge from Tokyo to Vancouver, I hope all of you will say that, no, that's not really doable. Nobody can build that bridge. However, if I ask you the same complexity in terms of software, you will have people banging on the door, shouting that they will do it for half the price. And why is that so? Simply because the human is not very good at judging logical complexity. Humans grew up judging physical complexity. Like if I, for example, tell you that I can throw a stone from here in Canada to Graz, you will laugh at me and say that's not doable because you understand it's not doable. But if I tell you the same thing in terms of software complexity, people might believe it. Actually, a lot of people might believe it, and they will start bidding on these contracts. And that's what you currently have in modern vehicles. To convince you on the theoretical level, I show you the Busy Beaver challenge. It is a very nice challenge where you can immediately see the limitations of the human mind in terms of understanding logical complexity. The Busy Beaver is essentially a challenge where you have to create the large machine that takes the largest number of steps taken by an end-state M symbol machine, where you start off with an initial blank tape. So let's look at the Turing machine for the Busy Beaver with 2 states and 2 symbols. And it's not really important that you understand now exactly how this works, but what I can tell you is that this particular machine here takes 6 steps before it terminates. And it's important that it terminates because everybody can build a machine that is an infinite loop and take an infinite number of steps. So remember, 2 states, 2 symbols, at most 6 steps before it terminates. Now let's look at another example, the busy beaver with 5 states and 2 input symbols. So you can see this as building a system that has 5 buttons and that has basically just a 0 or 1 going around in the system depending whether a button is pushed or not. And to make your life simple, I show you the busy beaver here on the right. Now the question is of course for you, how many steps do you think will this machine take before it terminates? And I can give you a guess, or I give you a hint. It is more than 6. It is more than 60. It's actually more than 6,000. It's more than 600,000. It's more than even 6 million. It is 47 million steps that this busy beaver that you see here will take with these 5 states and 2 symbols. So in order to really have seen everything, you would have to transition through 47 million steps. Well, but that's a busy beaver with 5 states and 2 inputs. Let's switch this around. Let's take one where we have just 2 states and 5 inputs. So you have the letters A, B, C, D, E and in your inputs, and you have 2 states. How many steps do you think does the currently best known busy beaver take in this particular example? And I will give you again a hint. It's more than 47 million. It's actually more than 47 trillion. It's more than whatever, 47 gazillion something. You can think of some very large number and you will be wrong. The current best known busy beaver in this particular configuration has 10 to the 704 steps. That's more atoms than they are currently estimated to be in our universe. So here you can see how quickly things can get extremely complicated and extremely complex without us even thinking that they would reach that particular level of complexity. And this here is good news for all the software developers and all the program and software managers, because now they have something that they can communicate to their upper peers and tell them, well, you know, it's actually very complicated what we are doing. However, the complexity of software is not the only challenge that we now have in our systems, especially now that we also network these systems, meaning that we allow these systems to talk to other systems. That causes a particular challenge for safety and security. Because we connect these vehicles now to an infrastructure, we allow attacks to be scalable. This means previously I had to walk up to every single vehicle that I wanted to attack and then, crawl underneath the vehicle, tinker a little bit with it and do something. Now that they are connected, if I'm able to find an exploit in the communication side, and then, for example, an exploit also in the infotainment system that has been shown in the past years, then I can reach, for example, all vehicles of a particular manufacturer or all vehicles of a particular model, and I can exploit potentially a vulnerability in there and attack all of them while I still sit in my basement. And that is, of course, a scary thought. Another observation is that software is now becoming a dominant problem for safety. And that, of course, also shows us that it is a dominant problem for security. In this particular figure, you can see the growth of recall reasons in the software area over the years. We looked at recall data from NHTSA, from RAPEX, and also from the Canadian Transportation Agency. And you can see clearly that there is a growth of recalls due to software. It's great because now we know that fewer people are burning up in cars due to, for example, exploding tanks. But the problem is, of course, now that over 30% of all of the recalls are due to software. Another important observation is that safety deals with the universe and security deals with people. What does this mean? Safety deals with problems like, for example, the sun flipping bits by chance. We can build models for this. We can understand how often this happens. Security, on the other hand, deals with attackers flipping bits on purpose. And now all of a sudden, all these nice models with respect to reliability are not applicable because the attacker might flip 2 bits in 2 different locations at the same time in order to enable a particular attack. That's why safety deals with the universe and security deals with people. Here you see a vehicle that is safe but not secure. And the reason is because there's an attack that has been demonstrated on this particular vehicle. Now, of course, there are patches out there for this, and millions of people have been driving this vehicle, and it's still considered safe because it has been developed to all the safety standards. Here you see a vehicle that is secure but not safe. Nobody would drive this particular car except Colin Firth, who has developed it. It's what you see here is a vehicle that essentially has a bubble foam bath included in the vehicle. It is secure because you can't really connect to it. It's an old vehicle and you can't really reliably attack it and then over the air. But of course, it is not safe at all. And there you can already see that you can build a safe and not secure vehicle and a secure vehicle that is not safe. Another observation is that safety is static and security is dynamic. Safety is static because when you follow all the process for it, then you will end up with a system that you would consider safe at this particular point. So once a safe product, always a safe product. Of course, there might be always new insights and some crazy behaviors that you might have not foreseen and that requires an update. But overall, once a safe product, always a safe product. For security, this is definitely not the case. Here you can see the vulnerabilities that have been disclosed over the years from the Common Vulnerabilities and Exposure Database, and you can see a stark increase in vulnerabilities that are being disclosed. That's not necessarily because we write less secure software, it's simply because software is becoming more visible everywhere, and it basically drives everything that we use in our daily lives. The interesting thing about this statistic is that, well, if you average it over the last 10 years, then you see 236 new vulnerabilities being disclosed per week. That's 1.4 per hour. So your product that might be considered secure on the day that you ship it might not be secure 1.4 hours after it. And that's actually only the publicly disclosed exposures. Now, there might be other vulnerabilities that held back or that are, for example, sold on the market that are not even part of these disclosed vulnerabilities yet. The key message is that security is dynamic and safety is relatively static. Another observation that we made over the years is that the durability of systems is really challenging some of the assumptions. When you look at a mobile phone, currently the companies are basically trying to convince you that after 1 year your mobile phone is outdated and you need to get a new car. On the other hand, on the cyber-physical systems domain, some of the systems that we have are operating since the 1950s. And remember, we have 206 new vulnerabilities per week, and that number is increasing. So what does that mean for your system that has been operating out there for a very long time? And vehicles are getting there. You will have vehicles in the field that are produced today still in 20 years from now. Who is going to patch the bugs and the software vulnerabilities in these vehicles? And there we get to an example that I like a lot, which is the highly automated oldtimer, which is basically in 30 years from now, 40 years from now, people will be driving Tesla Generation 1 vehicles or other types of vehicles that have like first versions of parking assist or super cruise built in, and they will be very proud of their vehicles. But what about all the software that runs in there? Has anyone updated the firmware? Has anyone fixed the vulnerabilities? Who will be doing this? It is a fundamental challenge that the industry still needs to think about how they are going to address this. Because you can't make a lot of money off these old vehicles, but they're still on the road and they will be on the road. So what do you do from an economic and commercial and business side, besides, of course, all the technical challenges of being able to compile software for a 20-year-old platform where your compiler might not even be existing anymore? So the highly automated oldtimer is something that will definitely be a topic for the next generation of engineers in the automotive space. Another major challenge is that systems must function continuously under all circumstances. Attacks, however, only have to work in a particular instance. So when you look at, for example, autonomous vehicles, and here you can see the Renesas autonomous vehicle demonstrator that we built at the University of Waterloo with Renesas, then it's a very complex system. You can see that it has a lot of different functionality blocks and a lot of different systems. And of course, you want this system to work on all circumstances, because you want it to be an autonomous vehicle where you can just sit in, watch the scenery, and have the vehicle drive you from one place to another. So this means you have to also cover corner cases, like this case here, close to the hospital here in Kitchener-Waterloo that I encountered. If you come out of the parking lot, you can interpret this at, well, you definitely are not allowed to go straight. You are definitely not allowed to do a right turn, and you're not allowed to do a left turn either. Well, that's most likely because the sign is bent, but still it's unclear at this point. However, your solution has to cover also these corner cases. And there are many other corner cases. Here's a picture I took driving from the airport back to Waterloo, and it looks like that truck is coming at you, but actually this truck is being towed. Or you have cases like this where you're driving in snow and still all your sensors have to somehow work, or your functionality has to work in a particular way. Or you have this case that where I took a picture when I was driving in Austria. This is actually from Munich airport on the way to Passau. And it's, well, slightly confusing. Where are your lane marks? And it would be interesting what the current algorithms choose in this particular scenario. So again, the message is that whatever you do on the safety side and on the regular function side, it has to work in all cases, in all common cases, and also the corner cases. Attacks definitely do not. So for example, an attacker can create garbage input that might only work and fool the system in some incidences and some cases. However, in those cases, the attack would be successful. And here you can see some pictures of a famous paper that was about basically attacking deep neural networks with garbage inputs and what then that network thought it would see, whether that's now a robin or a baseball or a peacock and so on. And there's also the work on stop sign vandalism that shows how non-robust and fragile our algorithms currently are, and how small modifications on signs can lead to different interpretation of the stop signs by a vehicle. So an attacker just has to find one configuration where to place the stickers to trick a computer system, or only a particular model, and then has a particular attack. Whereas again, on the safety side and on the defender side, you have to consider all these cases and still make sure that your system is always operating as well. Then there is also this work on mobile buy and the follow-up where you could just fly a drone and project some image. And it's something that is very difficult to handle because vehicle needs all of a sudden depth perception and needs to consider these cases as well. An attacker has to only find one particular instance where this works in order to fool a particular system. So attackers have the advantage over defenders that they do not have to keep the operator safe. They do not actually have to ship a product where it has to work in a large number of cases. It only has to work, for example, with one firmware in one configuration under one kind of weather condition in order to be a problem for the manufacturer of that vehicle. And this advantage is a fundamental problem for any security solution in the cyber-physical space, because a cybersecurity solution is not allowed to limit the operations of the system or cause an unsafe scenario, whereas the attackers can do whatever they want and it only has to work in some cases. So we have been building an IDS for some time here based on side channel information. And based on this, I would like to pass on a couple of insights and lessons learned from it. Overall, when you build CAN bus intrusion detection, then there are many different ways how you can build it, whether it's a gateway system or you use signatures, or you specify a model of like the physics and then you build your cybersecurity around it, or you learn, for example, the behavior. Doesn't matter. All of them roughly fall into this category of problems that I will outline in the next couple of slides. Here you can see our surrogate system, which was an old Sterling truck. It's nice because if we blew it up, and actually, yes, it's broken down by now, it's not a big loss because the vehicle just cost a couple of $1,000s, and we were able to instrument it, do things with it that we wouldn't be able to do with a much more expensive modern system. Also, in this talk, I'm not going to talk about the details of how our side channel based intrusion detection method works and how our sender authentication method works. You can look this up in papers. What I would like to convey are the insights and the lessons learned that also then translate into, for example, other types of intrusion detection systems and security systems that you have in the cyber physical systems domain. So, to jump right at the number one problem, it is false positives. A lot of people and a lot of also papers, and we also looked into this, of course, are trying to build learning models where you learn normal behavior and then try to find anomalies. Now, the major challenge that you have with this is that false positives in the cyber physical domain have a fundamental problem. If you, for example, even have a very good system, meaning a system with a very low false positive rate, so here 10 to the minus 6, that means 1 in 1 million messages is a false positive, you still have a huge problem. If you have 1 in a million messages as a false positive and you send 1,200 messages per second, that means you get 13.8 false alarms per hour on a single bus. So if you operate a fleet of trucks and they're driving 10 hours a day, which is not what they're driving more like 20 hours a day, then you get over 100,000 false positives in a single day. Now, I would like to encourage you to go into the literature and look at these works that what people report as false positives on their works and on their papers. They are nowhere near 10 to the minus 6. And so it is a big problem that we have false positives with any kind of learning-based model. And alarm fatigue is a real thing that has been shown in the medical domain. And of course, it also applies to the automotive domain. Just think about driving from Graz to Vienna. And I think the drive is about 2 hours or so. And you get basically 26 times the alarm goes off and says, you're under attack, you're under attack. Like, you would not listen to that thing at all and you would turn it off. One question is, of course, where do these false alarms come from? And one big problem is that you assume that you have a specification of the system. Now, automotive systems have very good specifications. You always work between suppliers and then, for example, OEMs, you have DIAs and you have clear specifications. But these specifications might still be incomplete at some point, they might be outdated, or they might simply be missing some things. And the problem is, for example, intrusion detection, whenever you see something outside of your specification, you may shout and raise an alert that something is going on. And so what should you do with a message that should not occur but still occurs? And we had this problem in many cases where we saw a message on the bus and we asked the industry partner and said, well, what does that message do? And because it was more truck-like system, well, they bought components from them and said, well, that must be one of the additional messages there, but we shouldn't raise an alert because of that. So one challenge is that, besides the false positives, is that you have often underspecified systems. Another challenge is that you might get corrupt data. And the question is, what do you do? Is it a fault or is it an attack on your system? So the assumption that a lot of people make is that all normal messages are transmitted correctly. And you can see this always in the literature when you see people training their networks or their intrusion detection systems, and then they basically have them all in digital form. But we looked at our system worked in a real vehicle on a real bus. And you might be surprised, but ECUs send garbage every so often. And what do you do when they send this garbage? Yeah, the ECUs might throw away the message, or they might not. You don't know whether that particular garbage message is a particular attack that is using a flaw in one of the transceivers, or whether it's really just a garbage message. And so should you discard it or should you shout? And then if you shout, it might be a false positive, and most likely it will be a false positive. And then you have again the challenge of many false positives in the system. One very interesting thing that we saw is, especially during the startup of systems and during the shutdown, they are very prone to sending garbage on the CAN bus. But again, the attacker might use exactly that particular element in order to set up an attack as soon as the vehicle is then running the next time. Another line of work works with models, modeling specifically the physics of a system. And the major challenge that you have is that you have a trade-off between the detection capability and how much tolerance you have for different use cases of the same system. Because when you look at modern vehicles, they are used in a large variety of contexts, climates, and driving conditions. Like you can see here in this picture. Of course, that's an extreme case, but still a vehicle is operating or should be operating in this case. Or if you suddenly have, for example, chains on your tires, the vehicle dynamics are very different. Now, are you currently under attack or did somebody put chains on there? Or, well, you might just pack 2 canoes on there, and again, your vehicle dynamics might change a lot, and all your models might not recognize this if they don't have enough tolerance. But if they have a lot of tolerance built in, then you can use this, or an attacker can use this to attack the system. And that's where the challenge is, that you have so much variety how the system is being used that it is very difficult to build models that have good detection capability and don't basically have a lot of false positives. And then you have this problem of how to respond if a security alert happens. So if you raise an alarm, everything is good, now what? What should you do in this particular case? Should you continue driving, allow the driver to continue? Think about it. Would you allow the driver to continue? If so, you have a problem, because the attacker just makes the driver drive off a cliff. Should you stop driving and basically disallow the driver to drive? Well, then you have a problem in this particular case, because unfortunately the wildfire and the smoke from the wildfire clogged filters or some sensors, and now the vehicle thinks it's under attack because of that, and then the vehicle shuts down in the middle of a forest fire. So you can clearly see that it's not that you never have necessarily just the right answer immediately at hand. It depends on the context. And that's very difficult to understand, because you not always get all the information to make the right decision and make the right decision quickly enough. And that's why responding to a security problem or a security alert in a cyber-physical system is still a significant challenge. And maybe we have to look at different approaches so that we say, well, if we can't get like 100% true positives and no 0% false positives, like for example, you would get in a signature-based approach, maybe we can not save a single vehicle, but we can always save the crowd. So we allow that a single system can be successfully attacked and can be, well, unfortunately be damaged. However, the whole fleet will not be able to be attacked at the same time. And that's a different concept. And then when you think about it this way, then you suddenly think also about different types of detection systems and protection systems. In the last part, I want to talk about the next frontier, and that is supply chain dependability. Supply chain dependability deals with this particular problem of, can you trust the hardware that you purchase from out of the region? Do you actually get what you ordered? Why is it a challenge? Well, on the one hand, we currently have a problem with recycled e-waste that is sold as new. So you will get a couple of processors that have been desoldered from other e-waste, and they are being sold to you as new. So all your safety assessment goes out of the window. You might have a problem with counterfeit chips, that somebody just basically replaces chips and makes cheap knockoffs that might not behave always the same way. And of course, you have the security problem of hardware implants as well in these systems. What we did in our research group is we looked at a famous example, which is the FTDI chip, which is a USB to serial converter from FTDI, and the so-called super real chip, which is a well-known counterfeit for this particular chip. And here you can see when you decap them and you look at them, then of course you can see the differences, but you cannot always decap every single chip and every single system, because then you will never ship a single system. So what we did is we basically use side channel analysis to analyze these systems. And now we can also do it with larger assemblies to basically look and compare a system that you receive to a particular baseline. We use side channel analysis on this to measure electromechanical parameters about the system to then basically tell you whether you should use this system or whether it is a counterfeit or, for example, a suspect part. Now, when you compare our approach, because it uses side channel analysis, it's completely black box outside, to other approaches, you can see that it's very good once you have a particular baseline. And to establish the baseline, the visual inspection is still the most trusted version to do this. However, once you have the particular baseline, our system works very well compared to other approaches, whether that's now RFID, X-ray, or power profiles. What we did is we bought a lot of FTDI chips from the market, in total 220 chips, and we bought them from different vendors, some authorized vendors, some auction vendors. And we then looked at them, we took X-rays from them, we did an in-circuit test, and also had a third-party tool to assess them to really establish the ground truth, whether they are authentic or whether they are counterfeit. And it turns out that 120 of them were counterfeits. And our method of side channel analysis of these chips was able to identify all 120 of them and basically sort out the 100 good ones from the 220 chips. So here you can see then a figure where how the clusters form, and you can see that we even identified non-functional chips as well, so they are large outliers. But not only that, we could detect counterfeit, we also were able to detect which counterfeit it was, because apparently there are multiple counterfeit makers out there for this particular chip. The system has a lot of applications in the supply tool chain. On the one hand, we plan to use it also in the collaboration with now AVL that we are setting up. The other part is, of course, the applications to identify counterfeit and also tampered parts. So that means when you're an OEM and receive parts, you basically just run them through a quick check, which takes a couple of seconds to assess whether this particular part is okay or not. It's also useful to identify undocumented hardware changes. You have a deal with your supplier and they agree to particular parts that they're going to use. You might want to check whether there is, for example, by accident, a particular change in their setting before you put the part into your system. And we have successfully demonstrated this with actually full ECUs in a particular system where we were able to identify unilateral changes behind individual pins. One of the elements that also astonished us how well the system works is that we were able to identify lot codes of chips, not of complete assemblies because you don't have a lot code for a full assembly, but for individual chips. And that means we are able to effectively allow you to enforce lot codes for your systems that you're building in case you need to blacklist, for example, particular lot codes because they have been produced already too far in the back, or basically they're too old, or because there was a known issue with a particular lot code. With the chip crunch right now everywhere and the supply chain problems, this is something you might suddenly get chips from somebody else, or some of your supplier might get chips from somebody that they just put on a particular board and then they sell it, and now you have these chips in your system. So essentially what this technology allows you is that you can ensure that what you got is actually what you ordered. And this is a key part of making sure that you have a safe and secure system. Because if you designed it to be safe and secure, you want to still make sure that when you manufacture it and when you then assemble it, it still is the system that you originally thought you would be designing and assembling. To conclude, we have an incremental transition from automated to autonomous vehicles. I don't think we will have a jump immediately to vehicles that have no steering wheel for the general population. There might be specific geofenced areas, specific application scenarios, like in front of at airports and so on, where you have this, but not in the general case. The second part is that systems are clearly becoming too complex for humans to comprehend. There is so much software and there are so many chips, so much networking in this distributed system that a single developer can no longer comprehend it. The other point that I wanted to bring across is that we need to ensure that we develop not only safe systems, but safe and secure systems. It's no longer enough to develop a safe system, because now that vehicles are connected and systems are connected, we need to have them safe and secure. Unfortunately, when you look at cyber-physical systems like connected vehicles, they heavily favor the attacker. The attacker just has to find one particular instance that works, whereas the security mechanism that you use on the defense side cannot interfere with the safety or the function of the system. And that's a major challenge. However, we found that side channel based assessment, whether that's now on, for example, a test stand when you receive parts, or that's on at runtime, are a very interesting new method of assessing the integrity of a system while it's operating. And overall, when you look at the supply chain, I think there's a lot of work that needs to be done there, because society at the moment really accepts a lot of risks through the supply chain, because we are not really looking at the supply chain yet in enough detail. And with this, I would like to close the talk, and I'm happy to take any questions.